What if the greatest mystery of the cosmos isn't what we can see, but what we can't? Picture the vastness of space, not the glittering stars or the swirling galaxies, but the stretches of absolute nothingness between them. These cosmic voids, these immense pockets of emptiness, hold secrets that defy our intuition. They're not just empty space, they're active players in the grand story of the universe, shaping its fate in ways more profound than the brightest supernova or the most massive black hole. Welcome to the astrophysics of absence, where nothingness becomes the most powerful force of all. Think about the last time you stared up at the night sky. Your eyes were drawn to the stars, right? But what about the darkness between them? That darkness isn't just a backdrop, it's a dynamic, almost alive phenomenon. Scientists have discovered that these cosmic voids, some spanning hundreds of millions of light years, aren't passive emptiness. They're pushing the universe apart, accelerating its expansion with a force we're only beginning to understand. It's as if the universe is being sculpted not by what's there, but by what isn't, and that revelation changes everything. This journey will take us to the edge of our cosmic understanding, where the rules of physics twist and bend in the presence of nothing. We'll explore how dark energy, the enigmatic force driving the universe's expansion, might be tied to these voids. We'll see how the absence of matter can warp the fabric of spacetime itself, creating effects so strange they seem ripped from science fiction. And most importantly, we'll confront a truth that redefines our place in the cosmos. Sometimes the most powerful forces aren't the ones that shout, but the ones that whisper in the silence. So let's dive in, because the story of the universe isn't just about what fills it. It's about the emptiness that shapes it all. The greatest trick the universe ever played was convincing us that nothing is truly empty. Those vast cosmic voids between galaxies, they're not just blank spaces waiting to be filled, they're seething with invisible activity. Quantum physics tells us that even in a perfect vacuum, particles flicker in and out of existence. A chaotic dance of energy and annihilation happening faster than we can measure. This isn't theoretical speculation. It's a phenomenon we've observed in labs, where so-called empty space crackles with imperceptible motion. And if that weren't strange enough, these quantum fluctuations might hold the key to one of cosmology's biggest mysteries: dark energy. Einstein was the first to wrestle with the idea that emptiness could have power. His cosmological constant, a term he later dismissed as his greatest blunder, turns out to have been eerily prophetic. He imagined space itself as a kind of elastic fabric capable of stretching or resisting. Today, we know that fabric isn't passive. The voids between galaxies aren't just expanding, they're pushing, accelerating the universe apart with a force that defies gravity. It's as if the universe is being stretched from the inside out by the very absence of matter. The more space grows, the more these voids multiply, creating a feedback loop of cosmic expansion. Here's the beautiful irony. The stars and galaxies we admire are mere passengers in this grand voyage, while the real engine lies in the emptiness we once ignored. Dark energy, that enigmatic force driving the universe apart, isn't radiating from some luminous source. It's woven into the fabric of nothingness itself. Scientists still debate whether it's a property of space or something even more exotic, but one thing is clear: the universe's fate hinges on what isn't there. So the next time you gaze at the night sky, let your eyes linger in the dark patches between the stars. That's where the real action is, where nothingness bends the rules, rewrites physics, and quietly steers the destiny of everything we know. The cosmos isn't just shaped by what we see, It's shaped by the absence we overlook, and that changes everything. Let's zoom in on one of the universe's most baffling structures, the cosmic void. These aren't just gaps in the cosmic web. They're colossal bubbles of near-nothingness, some so vast they could swallow thousands of galaxies without a trace. Take the Boötes Void, for instance, nicknamed the Great Nothing. This region spans 330 million light-years, yet contains only a handful of galaxies. If our Milky Way were placed at its center, we wouldn't have discovered other galaxies until the 1960s. That's how staggeringly empty it is. But here's the twist: these voids aren't static. They're growing, and in their expansion, they're reshaping the universe around them. How does emptiness sculpt the cosmos? Think of the universe as a stretchy fabric, where matter clusters like galaxies and galaxy clusters. The fabric dips, creating gravitational wells, but voids. They're the hills. As they grow, their edges push outward, creating pressure that literally shoves matter away. It's like blowing up a balloon with galaxies painted on its surface. The more the balloon expands, the farther apart those galaxies move. This push isn't gentle either. Voids can fling entire galaxy clusters toward denser regions, effectively herding matter into the universe's grand filamentary structures. The Boötes Void offers a perfect case study. Its extreme emptiness challenges our models of galaxy formation. According to conventional physics, a region that size should host at least 2,000 galaxies. Instead, it holds maybe 60. Some scientists speculate that the void might be a collision of multiple smaller voids, amplifying its emptiness. Others wonder if unknown physics, perhaps linked to dark energy, is at play. Whatever the explanation, one thing's clear: voids like Boötes aren't accidents. They're active players, their gravitational influence reaching far beyond their barren borders. Here's where it gets even wilder. Voids don't just move matter, they bend light. When light from distant galaxies passes through a void, it loses energy, stretching into longer, redder wavelengths. This integrated Sachs-Wolf effect is like the universe's fingerprint, proving that emptiness warps spacetime itself. And because voids dominate the universe's volume, making up over 80% of it, their collective push might be the reason the cosmos is expanding faster than expected. So while stars and galaxies steal the spotlight, it's the voids working behind the scenes, pulling the universe's strings. They're the silent architects, carving out the cosmic web structure one expansion at a time. And as we map more of these emptinesses, we're not just studying space, we're decoding the universe's hidden blueprint. If dark matter is the universe's invisible scaffolding, holding galaxies together like cosmic glue, then dark energy is its polar opposite, a shadowy force that thrives in emptiness, relentlessly pushing the universe apart. While dark matter clusters where galaxies gather, dark energy dominates the voids, growing stronger as space stretches. It's the reason our cosmos isn't just expanding but accelerating, as if some unseen hand is pressing harder on the gas pedal with every passing moment. And the strangest part, the emptier space becomes, the more powerful this force grows. The leading explanation for dark energy traces back to Einstein's infamous cosmological constant, a mathematical placeholder he added to his equations to describe a static universe. He later abandoned it when evidence showed the universe was expanding, calling it his greatest blunder. But modern cosmologists think he might have been onto something. The cosmological constant suggests that empty space isn't truly empty. It's imbued with a faint, unchanging energy density. As the universe expands, more space appears, and with it, more of this latent energy. It's like blowing up a balloon with a built-in anti-gravity effect. The bigger it gets, the faster it inflates, but not everyone's convinced. Some theorists propose an even wilder idea. quintessence. Unlike the static cosmological constant, quintessence is a dynamic, evolving field that could change over time. Imagine it as a cosmic weather system, with regions of higher or lower energy density subtly altering the rate of expansion. One day, this energy might weaken or even reverse, collapsing the universe in a big crunch, or it could intensify, tearing spacetime apart in a big rip. The fact that we don't know yet that dark energy remains this profound mystery is what makes it so thrilling. Here's the kicker: dark energy doesn't just exist in the voids, it creates them. As it accelerates the universe's expansion, it stretches matter thinner, amplifying the emptiness between galaxies. It's a self-reinforcing cycle. More emptiness means more dark energy dominance, which means even faster expansion. And if this continues, the distant future of the cosmos might be a cold, lonely one, where galaxies are so far apart their light can never reach us. So while dark matter builds the universe's structure, dark energy is the ghost in the machine, rewriting its destiny from the shadows. Every time we measure a distant supernova or map the cosmic microwave background, we're piecing together the story of this enigmatic force. And with every answer, we uncover deeper questions, because in the end, the universe's greatest power might not lie in its stars or galaxies, but in the silent, relentless push of nothingness itself. The quantum vacuum is the universe's ultimate illusion, a stage where emptiness is anything but empty. At the smallest scales, space isn't a serene void. It's a turbulent ocean of particles flickering into existence and vanishing faster than the blink of an eye. These virtual particles are born from quantum fluctuations, borrowing energy from the fabric of spacetime itself before annihilating each other in a relentless dance. It's as if the universe has a hidden pulse, a heartbeat of creation and destruction happening everywhere all at once. And while this might sound like theoretical fantasy, we've actually detected its fingerprints in the lab. Place two metal plates incredibly close together in a vacuum, and the quantum foam between them gets squeezed, producing a measurable force, the Casimir effect. This tiny push is proof that so-called nothingness is teeming with invisible energy. Now, imagine this quantum chaos near the edge of a black hole. Here, gravity is so intense it stretches spacetime like taffy, tearing apart those virtual particle pairs before they can annihilate. One particle falls into the black hole while the other escapes as radiation. This is Hawking radiation, the slow leak of energy that causes black holes to evaporate over eons. It's a staggering idea. Even the darkest, most lifeless places in the universe are glowing with quantum activity. And if black holes aren't truly black, what does that say about the nature of emptiness itself? But the quantum vacuum's surprises don't stop there. Some theories suggest our entire universe might have sprung from a similar fluctuation, a bubble of false vacuum that inflated explosively in the Big Bang. If that's true, then the cosmos itself could be one grand quantum accident, a single speck of potential in an infinite sea of nothingness. And if it happened once, why not again? The multiverse hypothesis paints a picture of endless universes bubbling up from the quantum foam, each with its own laws of physics, its own version of reality. So when we talk about the void, we're not talking about absence. We're talking about a canvas humming with possibility, where particles wink in and out of existence, where black holes glow, and where whole universes might be waiting to be born. The quantum vacuum isn't empty. It's the universe's workshop, and the tools are everywhere hidden in plain sight. Black holes are the universe's ultimate paradox, regions where absence doesn't just exist but consumes everything in its path. Picture a place where gravity wins the cosmic tug of war so decisively that not even light can escape. That's the event horizon, the point of no return, where the laws of physics as we know them begin to unravel. Beyond this boundary lies the singularity, a one-dimensional point where matter is crushed into infinite density, space and time cease to function, and our equations simply give up. It's as if the universe has built a trapdoor into unreality, a tear in the fabric of existence where nothing becomes all-powerful. What makes black holes so fascinating isn't just their destructive force, it's how they warp the very stage they act upon. Imagine spacetime as a trampoline. Place a bowling ball in the center and the fabric dips. That's how planets and stars curve space, but a black hole. It's like dropping a lead weight so heavy it punches a hole straight through the trampoline. The distortion is so extreme that time itself slows to a crawl near the event horizon. If you watched a clock fall into a black hole, its ticks would stretch out until they froze entirely, a phenomenon called gravitational time dilation. Light from objects behind the hole bends around it like a lens, creating eerie mirror images in a process known as gravitational lensing. Even emptiness here isn't passive, it's a dynamic, twisting force. And then there's the singularity. This is where physics textbooks surrender. At the heart of a black hole, all the matter it's ever consumed is compressed into a point smaller than an atom, yet with the mass of stars. Density becomes infinite, gravity becomes infinite. The rules of general relativity and quantum mechanics collide here in ways we still don't understand. Some theories suggest singularities might be gateways to other universes or tunnels through space-time wormholes. Others argue they're cosmic dead ends, where information is lost forever, violating quantum mechanics' insistence that information can't be destroyed. It's a debate that's raged for decades, with Stephen Hawking even proposing that black holes slowly leak radiation, evaporating over eons. Yet for all their destructive power, black holes are also creators. Supermassive ones like Sagittarius, a star at the Milky Way's center, act as galactic anchors, their gravity orchestrating the dance of stars around them. When black holes collide, they send ripples through spacetime itself, gravitational waves we've only recently learned to detect. Even their jets, streams of particles shot outward at near light speed, can ignite star formation in distant gas clouds. So while they're the ultimate cosmic vacuums, they're also sculptors, shaping the universe in ways we're just beginning to grasp. Here's the mind-bending truth: black holes aren't just holes. They're the universe's way of pushing gravity to its absolute limit, revealing where our understanding of reality frays at the edges. They force us to confront the uncomfortable idea that absence isn't inert, it's a force that bends, breaks, and rebuilds the cosmos in its image. And as we peer deeper into their mysteries, we're not just studying space, we're staring into a mirror, reflecting the most fundamental questions about existence itself. The universe might not end with fireworks or collapse, but with a whisper, a slow, inevitable fade into darkness. As emptiness grows, stretching space thinner with every passing moment, cosmologists have sketched out several chilling possibilities for our cosmic finale. The first is the Big Freeze, a scenario where dark energy continues accelerating the universe's expansion until galaxies are so far apart their light can never reach us. Stars burn out, black holes evaporate, and the cosmos becomes a vast, frigid graveyard where even the background glow of the Big Bang cools to near absolute zero. It's not an explosion or a crunch, just an endless drift into silence. Then there's the Big Rip, a far more violent outcome. If dark energy's push grows stronger over time, it could eventually overpower every force in nature, even the bonds holding atoms together. Picture space stretching so fast that first galaxies, then stars, then planets are torn apart. In the final moments, molecules, nuclei, and even quarks would be ripped to shreds as the fabric of reality itself fractures. The universe wouldn't just grow cold, it would disintegrate, but perhaps the most haunting possibility is heat death, where the cosmos reaches maximum entropy. In this state, energy is so evenly distributed that no work can be done, no stars can form, and no life can exist. It's like a cup of coffee left to cool eventually. It reaches room temperature and stays there forever. The universe becomes a featureless sea of particles, too sparse and weak to interact. Time loses meaning because nothing changes anymore. What ties these scenarios together? The relentless dominance of emptiness. Dark energy thrives where matter is scarce, and as the universe expands, those empty regions grow, fueling the acceleration. Galaxies aren't just drifting apart, they're being pushed by the void itself. And if this continues, the cosmos might one day be so vast and sparse that even the memory of structure fades. Yet there's a strange beauty in this cosmic irony. The same force that birthed galaxies, that sculpted the universe into its intricate web, might also be the hand that unravels it. We're left with a humbling thought. The universe's fate isn't written in starlight, but in the silent, growing dark between the stars, and that darkness, it turns out, holds the pen. Einstein once called it his greatest blunder, but today, the cosmological constant stands as one of his most startlingly accurate predictions. In 1917, grappling with equations that suggested the universe should either collapse or expand, he inserted this mathematical fudge factor, a tiny repulsive force embedded in empty space itself. Its purpose to counterbalance gravity and keep the cosmos static, as everyone then believed it was. But when Edwin Hubble discovered the universe was actually expanding, Einstein famously dismissed the constant as unnecessary. Little did he know, he'd accidentally laid the groundwork for solving one of modern cosmology's biggest mysteries. Fast forward to the late 1990s, when astronomers made a discovery that shook astrophysics to its core. By measuring distant supernova, they found the universe wasn't just expanding, it was accelerating. Something was overpowering gravity, pushing galaxies apart faster and faster. That something, a force eerily reminiscent of Einstein's discarded constant. Suddenly, his blunder wasn't a mistake at all. It was the key to explaining dark energy, the enigmatic phenomenon now thought to make up nearly 70% of the universe's energy content. Here's what makes the cosmological constant so brilliant in hindsight. It suggests empty space isn't passive, it hums with a faint, intrinsic energy. Picture a quiet room seemingly silent, but actually filled with the faint buzz of fluorescent lights or distant traffic. Spaces like that, even in a perfect vacuum, quantum fluctuations ensure it's never truly empty. The constant quantifies this energy, proposing that as the universe expands, new space appears, and with it, more of this latent repulsive force. It's like pouring water into a glass that magically grows taller as you fill it. The more space there is, the stronger the push becomes. Yet the story doesn't end there. Some theorists argue the constant might be too simple. If dark energy's strength changes over time, a concept called quintessence, then Einstein's static version isn't the full picture. Others explore even wilder ideas, like extra dimensions leaking gravity into our universe, altering how emptiness behaves. What's undeniable, though, is the irony, a term born from Einstein's reluctance to accept an expanding cosmos now defines its runaway acceleration. So was it really a blunder, or a stroke of intuition so ahead of its time that even its creator couldn't see its truth? Science often advances through such twists where yesterday's mistakes become today's revelations. The cosmological constant reminds us that genius isn't about being right the first time. It's about leaving doors open for future discoveries, even when you don't walk through them yourself. And in this case, the door led to the most profound mystery of all, the universe's silent, invisible engine hidden in plain sight. At the smallest scales imaginable, the smooth fabric of spacetime we take for granted dissolves into chaos, a seething, turbulent froth known as quantum foam. Picture an ocean during a storm with waves crashing unpredictably in every direction. Now shrink that down to a billionth of the size of an atom, and you're close to what physicists believe the foundation of reality looks like. Here, spacetime isn't a steady stage. It's a boiling pot of microscopic fluctuations where tiny wormholes blink in and out of existence, where space itself twists and knots like a tangled shoelace. This isn't science fiction, it's the bizarre prediction of quantum mechanics when it collides with Einstein's theory of gravity. The idea of quantum foam emerged from a simple but profound question: what happens to spacetime when you zoom in far enough? In the everyday world, gravity shapes planets and stars with predictable elegance. But down in the quantum realm, particles defy logic, existing in multiple states at once or tunneling through barriers like ghosts. Reconciling these two worlds, gravity's smooth curves and quantum mechanics' frenetic uncertainty, has been physics' greatest unsolved puzzle. Quantum foam might be the missing link. Imagine spacetime as a sheet of glass. From a distance, it appears flawless, but peer through a microscope, and you'll see cracks and bubbles trapped inside. Quantum foam is like those imperfections, a froth of tiny, fleeting distortions that could explain how gravity operates at the smallest scales. Some theories suggest these fluctuations aren't just noise, they're the universe's building blocks. Loop quantum gravity, for instance, proposes that spacetime is woven from indivisible atoms of space like pixels on a screen. Each pixel vibrates, twists, and connects to others, creating the illusion of smooth geometry at larger scales. Other models, like string theory, imagine spacetime as a symphony of vibrating strings, with quantum foam as the dissonant notes lurking beneath the melody. What's astonishing is that these ideas aren't purely mathematical. Experiments like the holometer at Fermilab have tried so far unsuccessfully to detect the faint jitter of quantum foam by measuring whether spacetime is slightly fuzzy at tiny scales. The real magic of quantum foam lies in its potential to bridge the unbridgeable. Einstein's relativity describes gravity as the curvature of spacetime, while quantum mechanics rules the particle world with probabilities and uncertainty. Quantum foam could be where these theories shake hands, where spacetime's smooth fabric frays into quantum randomness. If proven, it would rewrite our understanding of reality, revealing that even the emptiest void is a cauldron of creation. Every black hole singularity, every Big Bang spark, might trace back to this turbulent foam, where the distinction between something and nothing blurs into irrelevance. So the next time you gaze at the night sky, remember, the vast, tranquil cosmos is an illusion. Beneath it all, spacetime is alive, twisting and bubbling with possibilities we're only beginning to imagine. The universe's greatest trick isn't hiding its emptiness, it's disguising the chaos that makes emptiness possible. Imagine staring at a distant galaxy through a funhouse mirror, except the mirror is a billion light-year-wide pocket of nothingness. This is gravitational lensing by cosmic voids, where emptiness doesn't just sit quietly, it twists the very light passing through it like a cosmic illusionist. While most lensing events are caused by massive objects like galaxy clusters bending spacetime, voids do the opposite. Their lack of mass creates a gravitational hill in spacetime, forcing light to climb out of this shallow well. The result, light loses energy, stretching into longer, redder wavelengths, an effect astronomers call the integrated Sachs-Wolf effect. It's as if the universe's empty patches are subtly red, shifting the light of distant objects, not by moving them away, but by sapping their energy through sheer absence. Now take the mysterious cold spot in the cosmic microwave background, a chilling anomaly about 70 times larger than our full moon's apparent size. When scientists first spotted this region, it defied expectations. The temperature there was just a fraction cooler than the surrounding afterglow of the Big Bang. One leading theory, a supervoid, an unfathomably vast emptiness spanning over 1 billion light-years, might be the culprit. As light from the early universe passed through this void, it lost energy, creating that eerie cold patch in our maps of the infant cosmos. If confirmed, it would mean this void isn't just empty. It's so immense that its gravitational shadow reaches across nearly 14 billion years of cosmic history. But here's where it gets even stranger. Voids don't just bend light, they warp time itself. According to general relativity, time runs slightly faster in regions of weaker gravity. Since voids have less matter, clocks there would tick quicker than in denser parts of the universe. It's a minuscule difference, but over cosmic distances, these tiny shifts add up. A photon traveling through a void for billions of years would essentially emerge younger than one taking a path through galaxy-rich space. Emptiness, it turns out, isn't just shaping what we see, it's subtly tweaking the universe's clock. What's truly humbling is realizing how much of our cosmic view might be distorted by these invisible lenses. When astronomers measure the expansion rate of the universe or map dark matter's distribution, they're seeing it through the funhouse mirror of voids. Some distant supernova might appear dimmer not because they're farther away, but because their light passed through a void that drained its energy. Even the cosmic microwave background, our snapshot of the infant universe, could bear fingerprints of these ghostly structures. So the next time you hear about the emptiness of space, remember, it's anything but inert. These voids are cosmic pranksters, bending light, warping time, and leaving their fingerprints on the most ancient light in existence. They force us to confront a radical idea that nothingness doesn't just exist, it acts, and in its quiet way, it's rewriting the rules of the cosmos. The cosmic microwave background is like the universe's first photograph, a snapshot taken when it was just 380,000 years old, a newborn blinking into existence. But this isn't just a hazy glow, it's a treasure map etched with faint temperature differences as small as 1 part in 100,000. These tiny fluctuations are cosmic hieroglyphs, spelling out where matter clustered and where it didn't. The hotter spots, those are the seeds of future galaxies and clusters, but the cooler patches, they're the footprints of absence, the voids that would one day stretch across millions of light years. Take the famous WMAP and Planck satellite maps. At first glance, they look like static on an old TV, random speckles of hot and cold. But buried in that noise is a pattern, vast, whisper-thin regions slightly cooler than their surroundings. These are the cosmic voids in their infancy, places where matter was just a little sparser than average. Over billions of years, gravity amplified these differences. The dense spots grew into galaxies, while the underdense regions ballooned into the voids we see today. It's staggering to realize that the Boötes void, now a yawning chasm of near nothingness, began as a barely perceptible dip in temperature, a faint cold spot in the afterglow of creation. But the CMB doesn't just record these voids, it interacts with them. When light from the cosmic microwave background passes through a modern-day void on its way to us, something extraordinary happens. The void's gravitational hill, remember, less matter means weaker gravity makes photons work harder to climb out, losing energy in the process. This shifts their light to longer, redder wavelengths, an effect called the late-time integrated Sachs-Wolf effect. It's as if the voids are reaching across time, imprinting their emptiness onto the oldest light in existence. Scientists have actually used this to hunt for supervoids, cross-referencing cold spots in the CMB with maps of today's cosmic web. Here's where dark energy enters the stage. Without it, voids wouldn't leave such a strong imprint. In a matter-dominated universe, their gravitational hills would gradually flatten as expansion slowed. But dark energy accelerates the universe's growth, stretching voids faster and making their hills steeper. That's why the integrated Sachs-Wolf effect is considered one of the best indirect probes of dark energy. It's literally the shadow that absence casts on the primordial sky. So the next time you see an image of the cosmic microwave background, don't just focus on the hotspots where galaxies were born. Look at the cold ones too. They're not just empty space, they're active participants in the cosmos, subtly reshaping the oldest light we can see. The universe's baby picture isn't just a portrait of what's there. It's a negative too, revealing the power of what isn't. And that duality between presence and absence, between the glow and the gaps, might hold the key to understanding everything. Nothingness isn't just the end of things, it's often the beginning. Take the edges of cosmic voids where the absence of matter doesn't stifle creation, it ignites it. Picture a desert where the only rain falls at its borders. In the same way, the sparse regions of voids compress surrounding gas and dust into dense shells, triggering bursts of star formation. These are the universe's pressure cookers, where the push of emptiness collides with the pull of gravity, sparking new stars where you'd least expect them. Astronomers call these rare, radiant outposts void galaxies, lone islands of light adrift in an ocean of dark. One of the most famous examples is MCG plus 0102, a spiral galaxy so isolated it's nicknamed the galaxy that shouldn't exist. Floating in the Boötes void, over 200 million light-years from its nearest neighbor, it defies every expectation. Most galaxies grow by cannibalizing smaller neighbors or merging with peers, but void galaxies like this one are cosmic hermits, forging their destiny alone. Their solitude forces them to recycle their own gas, burning through it slowly and birthing stars with unusual efficiency. The result, a population of stars that glow bluer and younger than their clustered cousins, as if the void itself has gifted them extended youth. But how does emptiness become a cradle for creation? The answer lies in the physics of collapse. When a void expands, it doesn't just stretch space, it shoves matter outward, piling it up at the edges like cosmic driftwood. These dense rims become stellar nurseries where gas clouds crumple under their own weight, igniting fusion in their cores. It's a paradox. The same force that tears the universe apart also seeds its rebirth. And sometimes these edge-born stars don't stay put. Simulations show that void galaxies can be flung into the abyss by gravitational kicks, leaving them stranded in the darkness like shipwrecked sailors, yet still shining. The most astonishing part, these isolated galaxies might hold clues to the universe's early days. Without the chaos of galactic collisions or the pollution of older stars, their chemistry is pristine, mirroring the conditions of the ancient cosmos. Studying them is like finding a fossil frozen in time, a glimpse into an era when galaxies were rarer and space was emptier. So while voids might seem like deserts, they're more like oases, where the very absence of everything else creates the perfect conditions for something new. The universe doesn't just build in the crowded cities of galaxy clusters. It also creates in the quiet corners, proving that sometimes the best place to shine is where no one's looking. For centuries, humanity has treated emptiness as a cosmic mistake, something to be filled, feared, or conquered. Aristotle declared that nature abhors a vacuum, and for nearly 2,000 years, Western science obeyed that decree, insisting empty space was impossible. Medieval thinkers imagined horror vacui, nature's terror of the void, as a force so potent it would make water cling to pumps or celestial spheres press inward to prevent even a whisper of nothingness. Even art embraced this dread, with Renaissance masters cramming every inch of canvas with detail, as if blank space threatened meaning itself. Our ancestors didn't just misunderstand emptiness, they waged war against it, equating absence with chaos, evil, or oblivion. Yet while humans were busy fearing the void, the universe was building with it. Every cosmic structure we admire, galaxies, nebulae, even the vast web of dark matter, exists because of emptiness. Voids aren't accidents, they're the scaffolding. When the first quantum fluctuations appeared in the newborn universe, the densest patches became galaxies, while the underdense ones stretched into voids. Far from being barren, these regions actively shaped everything around them. Gravity works both ways. Where matter clusters, it pulls. Where it's absent, it pushes. The voids between galaxies didn't just allow the cosmic web to form, they dictated its design. Modern existential dread mirrors this ancient paradox. We fill silence with noise, solitude with screens, and space with clutter, as if emptiness were a predator stalking meaning. Yet astrophysics whispers a radical truth. Nothingness isn't passive or malignant. It's the universe's most underrated architect. Take galaxy formation. Without voids, matter would clump uniformly, leaving no room for grand structures. Those empty regions act like cosmic repellers, herding galaxies into filaments and sheets. Even Earth owes its existence to an ancient void, the local bubble, a cavern of sparse gas carved by supernova, whose shock waves triggered the birth of our sun. The irony is profound. We fear voids as if they erase significance, yet they're the reason anything exists at all. Black holes shred matter into singularities, only to fire particle jets that birth stars. Quantum foam churns with virtual particles, proving even the vacuum teems with potential. And dark energy, the ultimate manifestation of emptiness, is quite literally rewriting the cosmos. Our terror of nothingness says less about the universe and more about our own fragility. We cling to matter, to light, to noise, because we mistake presence for purpose. But the cosmos knows better. It thrives on balance, on the tension between what is and what isn't. Perhaps that's the most humbling lesson. The universe doesn't share our horror vacui. It celebrates it. Every star, every planet, every life form is here because emptiness made room. So the next time you feel the weight of the void, remember, darkness isn't the enemy. It's the canvas, and without it, not even light would matter. Even in the deepest vacuum, where classical physics says nothing should exist, the quantum world hums with restless energy. This is zero-point energy, the baseline vibration of the universe, the irreducible buzz that remains when all other energy is stripped away. Picture a guitar string that never stops vibrating, no matter how carefully you mute it. At the quantum scale, particles behave the same way, jittering endlessly due to Heisenberg's uncertainty principle, which states that we can never perfectly pin down both a particle's position and momentum. This isn't just theoretical, we've measured it. The Casimir effect, where two metal plates in a vacuum inexplicably pull toward each other, proves that so-called empty space is alive with fluctuations. Those plates are squeezed by the quantum foam outside them, a tangible signature of the universe's hidden pulse. Now, imagine tapping into that infinite reservoir. The energy density of the quantum vacuum is staggering. Some calculations suggest a single cubic centimeter of empty space contains more energy than all the matter in the observable universe. The catch: harvesting it. Zero-point energy isn't like coal or sunlight. It's everywhere and nowhere at once, a background hum that resists extraction. Yet that hasn't stopped scientists and engineers from dreaming. One speculative concept involves dynamic Casimir effect devices, which could convert virtual particles into real ones by vibrating mirrors at near light speeds, effectively shaking energy loose from the vacuum. Another wild idea leans on quantum entanglement, where manipulating one particle instantly influences its partner, potentially allowing energy transfer across vast distances without loss. Then there's the elephant in the room, warp drives. Popularized by sci-fi, the Alcubierre warp drive proposal hinges on negative energy, a hypothetical substance that could bend spacetime into a traveling bubble. Where might such energy come from? Zero-point fluctuations. If we could somehow compress the quantum vacuum in front of a spacecraft while expanding it behind, we might create a spacetime wave capable of faster than light travel. NASA Eagleworks Lab has dabbled in these ideas, though the challenges are monumental. The energy requirements are astronomical, and the engineering borders on fantasy. Yet the mere possibility hints at a profound truth. The universe's emptiness might hold the keys to its greatest treasures. Critics argue these ideas flirt with perpetual motion machines, violating thermodynamics. But zero-point energy doesn't offer free lunch. It's more like a cosmic bank with infinite deposits and withdrawal fees. Extracting usable energy would require precise, energy-intensive manipulations, likely balancing what's taken with what's spent. Still, the potential is intoxicating. A civilization that mastered vacuum energy wouldn't just solve its power needs, it would rewrite the rules of physics, turning the void itself into an engine. For now, zero-point energy remains a tantalizing what if. But history shows that today's impossibilities often become tomorrow's breakthroughs. The quantum vacuum isn't just empty space, it's a frontier whispering promises of technologies we're only beginning to imagine. And if there's one lesson the cosmos teaches, it's this: where we see nothing, the universe sees possibility. To simulate nothingness, astrophysicists must first teach supercomputers to dream in cosmic scales. The Millennium Simulation, one of the most ambitious computational experiments ever attempted, didn't just model galaxies or stars, it recreated the universe's vast emptiness with staggering precision. Imagine a virtual cosmos the size of a planetarium, where every pixel represents millions of light years, and the empty spaces between glowing clusters aren't blanks but dynamic actors in the drama. By programming the laws of physics into mind-boggling arrays of processors, these simulations reveal how voids grow like bubbles in cosmic foam, their expansion accelerating under dark energy's invisible hand. The magic lies in the numbers: over 10 billion particles, each representing a chunk of dark matter, interacting in a digital space spanning billions of light years. As the simulation runs, gravity tugs these particles into filaments and knots, while the voids between them stretch and merge. Watching this unfold is like seeing time-lapse footage of the universe's skeleton taking shape. The Millennium Simulation didn't just match our observations of the cosmic web, it predicted where we'd find voids before telescopes even pointed at them. One of its most haunting revelations: the voids aren't random. They form a pattern, a honeycomb of absence echoing the quantum fluctuations of the Big Bang itself. But simulating emptiness isn't just about dark matter and gravity. Modern projects like Illustris TNG and UCHU incorporate gas dynamics, magnetic fields, and even supermassive black holes to paint a fuller picture. When dark energy is added to the mix, something extraordinary happens. The voids begin to win. Their growth outpaces the clustering of matter, stretching the cosmic web until galaxies are isolated islands in an ever-widening sea. These simulations have become crystal balls, letting astronomers fast-forward trillions of years to glimpse the universe's fate, a cold, sparse expanse where voids consume everything. Here's the twist: these digital universes have also exposed gaps in our understanding. When simulations assume dark energy behaves like Einstein's cosmological constant, they match observations beautifully until they don't. Certain voids grow faster or slower than predicted, hinting that dark energy might be more complex than a simple constant. Others reveal mysterious void galaxies that shouldn't survive their isolation, yet stubbornly flicker to life in the code. Each discrepancy is a clue, a whisper that the physics of nothing might hold secrets we've yet to uncover. What's truly remarkable is how these simulations blur the line between science and art. The algorithms that render voids could power the next generation of video games or CGI, except instead of dragons or spaceships, they're sculpting the birth and death of the cosmos. The next time you hear about a supercomputer modeling the universe, remember, it's not just crunching numbers, it's teaching us to see the invisible, to map the unmapped, and to finally understand that nothingness isn't the absence of everything, it's the stage upon which everything dances. Imagine trying to solve a cosmic mystery where the clues aren't hidden in the stars, but in the silent stretches between them. That's the puzzle facing missions like the Dark Energy Spectroscopic Instrument, or DAISY, and the European Space Agency's Euclid telescope. These aren't your average space observatories, they're cosmic cartographers, meticulously mapping millions of galaxies not to study the galaxies themselves, but the voids they outline. Their goal: to catch dark energy in the act, revealing how it stretches the universe from the shadows. DAISY, perched atop a mountain in Arizona, is a technological marvel. Every night, it trains 5,000 tiny robotic fibers on distant galaxies, capturing their light like a celestial net. But here's the genius: by measuring how these galaxies move apart over time, DAISY isn't just tracking expansion, it's recording the universe's acceleration. The real magic happens when scientists cross-reference these motions with the voids between galaxies. As dark energy pushes space apart, voids grow faster, leaving a gravitational fingerprint on their surroundings. It's like watching invisible hands stretch a rubber sheet. You can't see the hands, but you can measure the ripples they leave behind. Meanwhile, Euclid takes a different approach. Orbiting 1,000,000 miles from Earth, this space telescope captures razor-sharp images of galaxies across a third of the sky. But its secret weapon is spectroscopy, splitting starlight into rainbows to measure precise distances. By combining these distances with galaxy positions, Euclid creates a three-dimensional map of the cosmic web, with voids as the negative space, the mission's true target. The subtle lensing effect, where voids bend light from galaxies behind them. This distortion, invisible to the naked eye, encodes dark energy's strength. If voids are the universe's fingerprints, Euclid is the detective dusting for clues. What makes these missions revolutionary isn't just their scale, it's their strategy. Previous dark energy hunts focused on supernova or galaxy clusters. DAISY and Euclid flip the script, treating emptiness as the main event. They've already uncovered tantalizing hints. Early DAISY data suggests dark energy might not be perfectly constant, as Einstein's cosmological constant predicted. Instead, it could vary slightly over time or space, a wrinkle that could upend cosmology. Euclid's first images, revealing ghostly tendrils of dark matter threading through voids, hint that our maps of nothingness are still missing pieces. The irony is delicious. For centuries, astronomers trained their telescopes on light. Now, the greatest breakthroughs might come from studying the dark. As these missions peel back layer after layer, they're proving a profound truth. To understand the universe, you can't just look at what shines. Sometimes the answers whisper from the gaps. What if the voids between galaxies aren't just empty space but gateways? The idea that our universe is one bubble in an infinite cosmic foam of parallel realities might sound like science fiction, but it's grounded in cutting-edge physics. According to bubble universe theory, the multiverse could be a sprawling ocean of universes, each with its own laws of physics, separated by stretches of primordial nothingness. And those gaps between worlds, they might look eerily similar to the cosmic voids we see in our own universe. Take inflation theory, the idea that our universe underwent a rapid exponential expansion just moments after the Big Bang. Some cosmologists suggest this inflation never truly stopped. Instead, it's happening endlessly in a larger multiverse, with new bubble universes constantly budding off like soap bubbles in a sink. These bubbles would be forever out of reach, isolated by expanding voids of false vacuum regions where space itself exists in a higher energy state, creating an impenetrable barrier. But here's the twist: if our universe is also surrounded by such a void, could we be staring into the abyss between realities every time we look into deep space? The math is tantalizing. In some models, cosmic voids share uncanny similarities with these theoretical bubble walls. Both are regions of lower density, both exert a repulsive gravitational effect, and both stretch spacetime in ways that defy conventional physics. Even stranger, certain anomalies in the cosmic microwave background, like the infamous cold spot, could be scars from collisions with other bubble universes in the distant past. It's as if the voids we see today are cosmic bruises, remnants of a multiversal fender bender billions of years ago. But how would we ever prove it? One clue might lie in the way voids distort light. If a neighboring universe brushed against ours, the gravitational waves from that collision could leave faint ripples in the polarization of the CMB, a signal experiments like the upcoming Light-Bird satellite are designed to hunt. Another possibility involves quantum entanglement. If particles in our universe somehow remain linked with their counterparts in another bubble, their synchronized behavior could betray the presence of a hidden cosmos. The most mind-bending implication: if voids are borders between universes, then the emptiest places in existence might be the most crowded. Every direction we look, beyond the farthest galaxies, beyond the coldest voids, there could be infinite other realities, each with its own version of space, time, and perhaps even life. Our universe's loneliness would be an illusion. The void wouldn't be empty. It would be a hall of mirrors, reflecting versions of existence we can't yet imagine. So the next time you hear about the Boötes void or the Great Nothing, don't think of them as dead ends. Think of them as windows, panes of frosted glass separating us from the impossible. The universe's greatest secret might not be written in the stars, but in the silence between them. And if we listen closely, the void might just whisper back. Long before telescopes revealed the cosmic voids between galaxies, ancient philosophers were already contemplating the power of nothingness. In Buddhist teachings, the concept of sunyata, often translated as emptiness, doesn't mean mere absence. Instead, it describes a fundamental truth that all phenomena lack inherent, independent existence. Everything is interconnected, dependent on causes and conditions, like a cosmic web where nothing stands alone. Strikingly, modern astrophysics echoes this insight. When we peer into the vast voids between galaxies, we're not just seeing empty space, we're witnessing the scaffolding of the universe, the invisible framework that gives shape to everything that exists. The parallels run deeper. Both sunyata and cosmic voids challenge our instinct to equate reality with what we can see or touch. In Buddhism, emptiness isn't a void to fear but a creative potential, the ground from which all things arise. Similarly, astrophysicists now understand that cosmic voids aren't passive gaps, they're dynamic forces. They're gravitational push shaping the cosmic web as much as galaxies do. The great nothing isn't inert, it's a participant bending light, warping time, and accelerating the universe's expansion. Whether through meditation or mathematics, both traditions arrive at the same counterintuitive truth: nothingness isn't the opposite of existence. It's the canvas on which existence paints itself. Even the language overlaps. Buddhist texts describe reality as like a mirage or like a dream, emphasizing its fluid, interdependent nature. Modern cosmology, in turn, speaks of spacetime as a malleable fabric where matter and energy are fleeting ripples on a deeper quantum sea. The Prajnaparamita Sutras declare, "Form is emptiness, emptiness is form," a poetic mirror to Einstein's revelation that space and matter are two sides of the same coin, each shaping the other. When a void's gravitational hill bends starlight, or when quantum particles flicker in a vacuum, we're seeing the universe whisper the same lesson. What appears empty is alive with possibility. Yet there's a crucial difference. For Buddhists, sunyata is a call to let go of fixed views, to recognize the fluidity of all things. In astrophysics, voids are puzzles to solve, their mysteries quantified through equations and simulations. One tradition seeks liberation from illusion, the other seeks deeper understanding of physical law. But both, in their own ways, dissolve the illusion of separateness, whether between self and world or between matter and space. Perhaps that's the most profound meeting point. Both perspectives remind us that reality is far stranger than it seems. The next time you gaze at the night sky, try this. Don't just focus on the stars. Let your eyes rest on the darkness between them. In that emptiness, science and spirituality agree, lies the universe's deepest secret, not a blank void, but a fertile ground where everything and nothing is possible. Picture the universe as a grand cosmic ballet where galaxies don't just drift aimlessly, they're herded into colossal structures by the very absence around them. At the center of this dance are voids, those sprawling deserts of nothingness that don't just sit idly by. They push, they nudge, they sculpt, and nowhere is this more breathtakingly clear than in the Laniakea supercluster, our galactic neighborhood, a sprawling web of 100,000 galaxies stretching over 500 million light-years. But here's the twist: Laniakea isn't defined by the galaxies within it. It's shaped by the voids surrounding it. Take the dipole repeller, a vast void lurking beyond Laniakea's edge. This region of extreme emptiness isn't just a passive gap, it's a gravitational bulldozer. While the Great Attractor, a dense cluster of galaxies, pulls us toward it, the dipole repeller does the opposite. Its lack of mass creates a kind of anti-gravity hill, shoving galaxies away like a cosmic bouncer clearing a dance floor. The result: galaxies stream along invisible highways, funneled into the filaments and knots that make up Laniakea's web. It's as if the supercluster is a whirlpool with emptiness itself shaping the currents. This push and pull isn't unique to Laniakea. Across the universe, voids act like cosmic repellers, their boundaries pressing outward as they expand. Imagine blowing bubbles in a pot of honey. As each bubble grows, it displaces the sticky liquid around it, forcing it into intricate threads and sheets. That's essentially how the cosmic web forms, except instead of honey, it's galaxies, and instead of soap, it's dark energy stretching the voids ever larger. The Sloan Great Wall, a filament of galaxies over 1 billion light-years long, arcs around a chain of voids like a bridge spanning canyons of nothingness. Even the Virgo cluster, our local gathering of galaxies, sits at the intersection of multiple void-driven flows. But here's where it gets even wilder. Voids don't just shape superclusters, they give them life. As galaxies are funneled into filaments, they collide, merge, and ignite bursts of star formation. The densest knots become galaxy clusters, glowing cities in the cosmic web. Meanwhile, the voids grow emptier, their expansion accelerating as dark energy's influence strengthens. It's a self-reinforcing cycle. The more galaxies are pushed together, the more the voids between them stretch, and the faster the universe's structure evolves. So the next time you see a map of the cosmic web, don't just focus on the bright knots of galaxies. Trace the dark patches between them. Those are the true architects. The universe isn't just built by what's there, it's carved by what isn't. And in that delicate balance between presence and absence, between the push of emptiness and the pull of matter, the grandest structures in existence take shape. The universe could end not with a bang, but with a whisper, a single quantum hiccup in the fabric of nothingness. This is vacuum decay, the most chilling doomsday scenario physicists have ever conceived. It begins with a startling realization. What we call empty space isn't truly empty, and worse, it might not even be stable. The quantum vacuum we've come to know, buzzing with virtual particles, could be a precarious illusion, like a marble balanced on the edge of a cliff. Some theories suggest our vacuum is a false one, a temporary state that could, at any moment, collapse into a lower energy, true vacuum. And if that happens, the universe as we know it would vanish faster than the speed of thought. Picture this, somewhere in the cosmos, perhaps in a distant galaxy or even right next to us, a tiny bubble of true vacuum forms. Inside this bubble, the fundamental constants of physics, the strength of gravity, the mass of electrons, even the nature of light are rewritten. The bubble expands at the speed of light, its walls racing outward like an unstoppable tidal wave. Every atom, every star, every law of physics it touches is instantly overwritten, reduced to a new, alien state. By the time the light from this catastrophe reaches us, it would already be too late. The wave front wouldn't just destroy Earth, it would erase chemistry itself, making life impossible in its wake. There would be no warning, no time to react. One moment the universe exists, the next it's something else entirely. What makes vacuum decay so terrifying isn't just its inevitability, it's the randomness. Unlike asteroid impacts or stellar collisions, this isn't a disaster we could predict or avoid. It could be triggered by a single quantum fluctuation, a tiny ripple in the fabric of spacetime that cascades into cosmic oblivion. Some calculations suggest the process might already be underway in some distant corner of the universe, its wave of annihilation racing toward us at light speed. We wouldn't know until it arrived, yet here's the twisted beauty of it all. Vacuum decay isn't destruction in the traditional sense, it's transformation. The universe wouldn't end, it would simply become something unrecognizable, governed by different rules. Atoms might not hold together, stars might not shine. The very concept of matter could cease to have meaning. In that sense, vacuum decay is the ultimate cosmic reset button, a reminder that even the laws of physics aren't set in stone. The irony is profound. We've spent centuries fearing black holes, supernova, and asteroid impacts, all while the most existential threat might come from the emptiness we've taken for granted. The quantum vacuum, once thought to be a passive backdrop, could be a sleeping dragon, and if it ever wakes, the universe as we know it will be nothing more than a fading echo in the dark. For decades, we've scanned star clusters and galaxies in our search for extraterrestrial intelligence, assuming advanced civilizations would flock to the cosmos's brightest hubs. But what if we've been looking in all the wrong places? The answer to Fermi's famous paradox, "Where is everybody?" might not lie in the glittering cities of stars, but in the deserts between them. Cosmic voids, those unimaginably vast regions of near-nothingness, could be the perfect hideouts for civilizations far older and wiser than our own. Think about it. If a species had mastered interstellar travel and energy harvesting, where would they thrive? Not in crowded galactic neighborhoods where supernova and black holes pose constant threats, but in the quiet expanse of voids. Here, the absence of competing stars means unlimited real estate and resources. A civilization capable of harnessing dark energy, the mysterious force accelerating the universe's expansion, could treat voids like infinite power plants, tapping into the very fabric of space itself. Instead of building Dyson spheres around stars, they might construct space-time altering megastructures that siphon energy from the void's expansion. The silence of SETI telescopes wouldn't be a sign of failure, just a sign we've been eavesdropping in the wrong rooms. This idea flips the Fermi paradox on its head. We assume advanced aliens would colonize galaxies visibly, leaving technosignatures like radio waves or megastructures. But what if they've evolved beyond the need for such crude markers? A void-dwelling civilization might communicate through quantum entanglement or manipulate dark matter in ways invisible to our instruments. Their technology could be so seamlessly integrated with the void's physics that it's indistinguishable from nature itself. The great silence isn't evidence of absence, it's evidence of a sophistication we can't yet fathom. Consider the Boötes void once more. If a single advanced civilization had emerged there billions of years ago, with no cosmic neighbors to compete with, they'd have had unimaginable time to grow. While Earth's life grapples with climate change and war, a void civilization might have solved entropy itself, transcending physical form to exist as pure information in the quantum foam. Their messages could be encoded in the void's gravitational waves or the subtle fluctuations of dark energy signals we lack the context to even recognize. The unsettling truth: voids might not be lifeless. They could be the universe's most advanced neighborhoods, their darkness not a void at all, but a cloak. And if that's the case, the silence isn't empty, it's listening. Imagine folding a piece of paper so two distant dots touch, then punching a hole through them. That's the essence of a wormhole, a cosmic shortcut where spacetime itself folds to connect two far-flung points. But here's the twist: these theoretical tunnels might not be forged from matter or energy, but from the very absence of them. Einstein and Rosen first dreamed up these bridges not as physical structures, but as mathematical quirks in the fabric of nothingness. Their equations suggested that under the right conditions, emptiness could twist into a tunnel, stitching together separate moments or places like a celestial sewing needle. Take the concept of negative energy, a bizarre quantum phenomenon where certain vacuum fluctuations behave as if they have less than zero energy. This isn't just theoretical wordplay. We've observed it in the Casimir effect, where metal plates in a vacuum inexplicably attract each other. Negative energy could be the key to propping open a wormhole's throat, counteracting the crushing force of gravity that would otherwise snap it shut. Picture a tunnel lined with this exotic energy, its walls repelling each other like magnets flipped the wrong way, creating a stable passage through the void. The strangest part: the tunnel itself might be made of almost nothing, just a whisper of distorted spacetime, a filament of absence stretched between two somewheres. But how could emptiness hold a tunnel open? Think of spacetime as a trampoline. Place a bowling ball on it, and the fabric dips. That's gravity warping space around a star. Now imagine pinching two distant sections of the trampoline together until they touch. The pinch itself isn't matter, it's a rearrangement of the fabric. In wormhole physics, the throat behaves similarly, a pinch in spacetime where the emptiness between points becomes the bridge. quantum foam, that frothy turbulence at the smallest scales, might spontaneously birth microscopic wormholes, flickering in and out of existence too quickly to detect. If we could somehow capture and stretch one, could we turn quantum nothingness into a galactic highway? The implications are dizzying. A wormhole built from voids wouldn't just bend space, it could bend time. Enter one end, and you might emerge not just elsewhere, but elsewhen. This isn't pure fantasy, the math allows it. General relativity permits solutions where wormholes function as time machines, their mouths aging at different rates if one's moved near a black hole or accelerated to near light speed. The catch: stability. Without negative energy, the wormhole collapses instantly. Even with it, the slightest disturbance, a single photon passing through, could trigger a catastrophic feedback loop, snapping the tunnel shut like a cosmic mousetrap. Yet if nature abhors a vacuum, it might adore a wormhole, a flaw in the cosmic glass where nothingness becomes the ultimate shortcut. So while black holes dominate headlines, their quieter cousins, wormholes woven from emptiness, might be the universe's true masterpieces. They hint at a cosmos where the shortest distance between 2 points isn't a line but a lacuna, where absence doesn't separate but connects, and where the void, far from being barren, could be the most crowded thoroughfare of all if only we knew how to look. When two black holes spiral toward collision, the universe doesn't just watch, it rings like a bell. These cosmic voids, regions where gravity has crushed matter into oblivion, don't merge silently. Their final embrace sends shockwaves through spacetime itself, stretching and squeezing the fabric of reality in a phenomenon we call gravitational waves. It's as if emptiness has a voice, and in 2015, for the first time in history, we learned to listen. The Laser Interferometer Gravitational Wave Observatory, or LIGO, didn't just detect these ripples, it translated them into sound. The signal from a black hole merger 7 billion light-years away reached Earth as a faint chirp, a fleeting vibration smaller than the width of an atom. But that tiny wobble told an epic story: two voids, each 30 times the mass of our Sun, whirling around each other hundreds of times per second before colliding at half the speed of light. In that moment, 3 suns worth of pure energy vanished into gravitational waves, leaving behind a single, more massive black hole, a new void echoing into the cosmos. What's astonishing isn't just the violence of these collisions, but what they reveal about nothingness. A black hole's event horizon is the ultimate boundary between something and nothing, and when two of them merge, the resulting waves carry fingerprints of the void's very shape. The pitch and decay of the chirp encode the black hole's masses, spins, and even the geometry of the spacetime they carved out. It's like hearing the silhouette of an invisible object, a sonic photograph of absence itself. LIGO detections have opened an entirely new sense for astronomy. Before, we studied the universe through light photons streaming from stars and gas. Now we can listen to the vibrations of spacetime, hearing events too dark or distant to see. Some black hole mergers occur in voids so vast that no starlight ever reaches us, yet their gravitational waves cut through the cosmic silence like thunder. Even more mind-bending, these waves subtly warp everything they pass through, briefly stretching every atom on Earth as they ripple by. You've been touched by the echo of a void and didn't even feel it. The most poetic twist: gravitational waves don't just come from black holes. Every massive object in motion creates them, from orbiting neutron stars to the birth of the universe itself. But black hole mergers are the loudest, their waves ringing clearer because there's no messy gas or light to drown out the pure geometry of spacetime. It's the difference between hearing an orchestra through a wall and listening to a single, perfect note sung in a vacuum. So the next time you see a silent night sky, remember, the cosmos is anything but quiet. The voids are speaking, we've just learned how to hear them. The universe didn't begin with a bang, it began with a stretch. Inflation theory paints a picture of the cosmos's first moments not as an explosion, but as a runaway expansion, where space itself ballooned from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. But here's the twist, this exponential growth didn't happen in a crowded, energetic furnace. It happened in something eerily close to nothingness, a primordial void where the very concepts of space and time were still stitching themselves together. Imagine a frozen lake on the verge of spring. Beneath the ice, unseen cracks form, spreading faster than the eye can follow. Inflation was like that, a phase transition where the vacuum of space, seething with potential energy, suddenly froze into the lower energy state we recognize today. As it froze, it released a cosmic windfall of energy, driving space to expand at speeds far beyond light's reach. But what's often overlooked is the starting point, a near void so uniform that even the laws of physics hadn't yet settled into their current forms. This wasn't just emptiness, it was a blank slate vibrating with quantum uncertainty, a canvas where every brushstroke would shape the fate of everything. And then came the whispers. Quantum fluctuations, tiny, random variations in energy rippled through this inflationary void. These weren't flaws in the fabric of reality, they were its blueprint. As space stretched, those microscopic wrinkles stretched with it, magnified from quantum shivers to cosmic mountains and valleys. The denser regions became the seeds of galaxies and clusters, while the underdense ones ballooned into the voids we see today. It's a staggering thought. The Boötes void, the dipole repeller, every gap in the cosmic web traces back to a quantum hiccup in the first sliver of a second. The universe wasn't just born from nothing, it was sculpted by its absences. The afterglow of this process is still visible in the cosmic microwave background, that faint echo of the Big Bang. Those tiny temperature variations, hotter spots where matter would later clump, cooler patches where voids would grow, are direct snapshots of inflation's quantum seeds. The European Space Agency's Planck satellite mapped these variations with precision, revealing a pattern that aligns perfectly with predictions. The kicker. The largest voids in today's universe correspond to the coldest, most underdense spots in that ancient light. The emptiness we see now was literally baked into the cosmos before stars or atoms even existed. But inflation's legacy goes deeper. Without those initial voids, galaxies might have formed uniformly, leaving no room for the intricate web we call home. Their gravitational push created the cosmic highways along which galaxies stream, the great walls and filaments that define the universe's architecture. Even dark energy, the force now accelerating expansion, might owe its existence to inflation's vacuum energy, a haunting echo of that primordial stretch. So when we stare into the voids, we're not just seeing empty space, we're seeing the universe's first draft, written in quantum tremors and frozen into the fabric of reality. The nothingness between galaxies isn't an afterthought. It's the oldest thing there is. Galaxies aren't supposed to move like this. In a universe where dark energy stretches space evenly in all directions, everything should drift apart smoothly, like raisins in rising dough. Yet something strange is happening on the largest scales. Scores of galaxy clusters, some billions of light-years apart, are streaming in the same direction at breakneck speeds, as if pulled by an invisible hand. Astronomers call this eerie synchronization the dark flow, and its existence hints at a cosmic imbalance so vast it defies everything we know about the universe's structure. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. As galaxy clusters race through space, their motion leaves a faint imprint on this ancient light, like wakes behind speeding boats. When scientists analyzed data from the Wilkinson microwave anisotropy probe, they found hundreds of clusters all moving toward a single patch of sky near the constellations Centaurus and Vela. The kicker, this motion couldn't be explained by the known distribution of matter. Whatever was tugging these galaxies lay beyond the observable universe's edge, in realms we'll never see. One provocative theory points to an unimaginably vast void, or rather, an absence of voids. Most of the cosmos is frothy, with matter clustered into filaments and walls surrounded by empty bubbles. But if there existed a region trillions of light-years wide where this foam didn't form, a supervoid of supervoids, its gravitational influence could be staggering. Picture standing at the edge of a canyon so deep you can't see the bottom. The lack of mass in that chasm would create a subtle but relentless pull, drawing everything toward it. Now scale that up to cosmic proportions. The dark flow might be our universe leaning toward such a void, a gravitational tilt etched into the fabric of spacetime itself. Critics argue the dark flow could be a measurement error or a statistical fluke. After all, the signal is faint, and the universe loves to surprise us with false patterns. But newer observations, including data from the Planck satellite, have only deepened the mystery. The flow persists, and its direction aligns eerily with other cosmic anomalies, like the infamous axis of evil, a controversial pattern in the CMB that some suggest hints at a pre-Big Bang structure. Could these clues all point to the same unseeable attractor, a void so colossal it bends the rules of cosmology? The implications are dizzying. If the dark flow is real, it means our universe isn't just lopsided. It's still feeling the gravitational tug of something from beyond the horizon of what we can observe. Emptiness, once thought to be passive, might be the puppet master behind the grandest motions in existence. And that raises an even wilder question. What else is out there, in the voids we can't yet see, quietly steering the cosmos from the shadows? Great artists understand a secret that astrophysicists are only now unraveling sometimes. What you leave out matters more than what you put in. Take the ink-wash paintings of ancient China, where a single brushstroke of black swirls into empty parchment, or the haunting compositions of Arvo Pärt, where the silence between notes carries as much weight as the music itself. These masters knew that absence isn't just background, it's the essence. In astrophysics, we're discovering the same profound truth. The voids between galaxies aren't blank margins in the story of the cosmos, they're the main text. Consider how we map the universe. For decades, astronomers focused on the bright object stars, quasars, galaxy clusters, as if they were the only characters worth studying. But in the 1980s, redshift surveys revealed something startling. Galaxies weren't scattered randomly. They formed a vast cosmic web with thread-like filaments surrounding enormous empty bubbles. Suddenly, the voids weren't just gaps. They were the architectural foundation. Like realizing a spider's web is defined as much by the holes between threads as the silk itself. The largest structures in existence, superclusters spanning hundreds of millions of light years, are shaped by the gravitational push of surrounding voids, their emptiness acting like invisible hands molding clay. This inversion of perspective changes everything. When cosmologists study baryon acoustic oscillations, frozen sound waves from the early universe, they're not measuring where galaxies are, but how their positions relate to voids. The pattern resembles ripples around a stone tossed in a pond, except the stone is an absence. Even dark matter, that elusive cosmic scaffold, maps more clearly around voids than clusters, because where matter isn't tells us more about gravity's workings than where it is. It's like diagnosing a lung by studying the air pockets rather than the tissue. the parallels with art run deep. In Mondrian's Broadway Boogie Woogie, the vibrant colored squares only dance because of the white spaces between them. In the universe, galaxies only cluster because voids push them together. Both systems obey a deeper harmony, one where presence and absence are partners in an eternal dance. The most revealing view of a cathedral isn't its stained glass, but the empty arches holding them aloft. Perhaps the ultimate lesson lies in quantum physics, where the vacuum isn't empty but seething with potential. The voids between stars may seem like nothing, but they're pregnant with dark energy, quantum fluctuations, and untold mysteries. Just as the white space in a haiku holds unspoken meaning, cosmic voids whisper secrets about the universe's birth, expansion, and fate. To truly understand the cosmos, we must learn to listen to its silence. We think of life as something that clings to planets, thriving in the warm glow of stars. But what if life's true pioneers aren't hugging the light, but embracing the void? The deepest cosmic deserts, those unimaginably vast regions where galaxies are almost absent, might seem like the last place biology could take root. Yet life on Earth has repeatedly proven it can flourish in places we once thought uninhabitable, buried under miles of ice, in boiling acid pools, even inside the crushing depths of nuclear reactors. If extremophiles can conquer those hellscapes, why not the void? Picture an organism not bound by the chemistry we know. Instead of relying on sunlight or geothermal vents, it might harvest energy from the quantum foam itself, the seething virtual particles that flicker in and out of existence in empty space. These hypothetical vacuum extremophiles could treat fleeting quantum fluctuations like a buffet, absorbing the minuscule energy bursts when particle pairs annihilate. Their metabolism would be slower than glacial, operating on timescales we'd perceive as frozen, with life cycles spanning millions of years. In a realm where time stretches and matter is sparse, evolution would favor patience over speed, efficiency over abundance. Or consider an even wilder possibility, life that feeds on dark energy. As voids expand, dark energy's influence grows, stretching spacetime itself. Could some form of existence tap into that relentless expansion, using spacetime's stretch like a cosmic windmill? Theoretical physicist Freeman Dyson once speculated about life surviving near absolute zero by exploiting quantum spin states. In the voids where temperatures hover just above the coldest possible, similar adaptations might arise. These beings wouldn't resemble anything we recognize, more like intricate patterns in spacetime, their bodies woven from gravitational waves or quantum entanglement. The real shock isn't just that life might exist in voids, it's how it would redefine life's boundaries. On Earth, water is life's universal solvent, and carbon its building block. But in the void, where molecules are rarer than stars in a supervoid, biology might abandon chemistry entirely. Information itself could become the substrate, with self-replicating patterns encoded in the quantum vacuum or dark matter's invisible web. Their DNA might be written in the spin of particles or the curvature of spacetime, their evolution driven not by competition for resources, but for stability in an ever-stretching cosmos. Here's the twist: if void life exists, we might have already detected it without realizing. The unexplained dimming of certain stars, the anomalous cooling of cosmic microwave background patches, even the mysterious alignment of galaxies in dark flow. Could these be signatures not of physics gone wild, but of biology operating on scales we're only beginning to imagine? The universe's greatest extremophiles wouldn't just survive the void, they'd master it, turning absence into abundance, silence into song, and in doing so, they'd force us to confront a humbling truth: life isn't just an accident of matter. It's a universal principle, as inevitable as gravity and far more creative. The equations that describe cosmic voids aren't just abstract symbols, they're the universe's own language for nothingness. Take Einstein's field equations, the heart of general relativity. At first glance, they seem to celebrate matter and energy, with terms for density and pressure dominating the page. But look closer and you'll spot the cosmological constant lambda, a term Einstein initially inserted to describe static space, then discarded. Today, lambda is the mathematical fingerprint of dark energy, representing the repulsive force of empty space itself. It's a number so small you'd overlook it on a calculator, yet it governs the fate of the cosmos. The irony is exquisite. The term meant to cancel expansion now drives it, proving that even Einstein's blunder was a whisper of truth. Voids play by their own rules in these equations. In tensor calculus, the mathematical machinery of relativity, they appear as negative curvature regions where spacetime isn't dented by mass but subtly bulges outward. Picture a trampoline with weights removed instead of added. The fabric doesn't sag, it rebounds. This anti-gravity effect is encoded in the stress-energy tensor, where voids have negative effective pressure, pushing galaxies apart like cosmic repellers. The math reveals a startling symmetry. Just as matter tells spacetime how to curve, absence tells it how to stretch. Dark energy's equations are even more counterintuitive. In quantum field theory, the vacuum isn't zero. It's a sea of fluctuating energy described by the zero-point energy formula. Each cubic centimeter of empty space crackles with virtual particles, their energy density theoretically infinite until renormalization, a mathematical trick that subtracts infinities to reveal finite, measurable effects. It's like balancing a checkbook where the numbers initially don't add up, but the universe has its own accounting system. The result, a vacuum energy density so tiny, 120 orders of magnitude smaller than predicted, that it borders on absurdity. Yet this discrepancy, called the cosmological constant problem, is the price tag on emptiness. The real magic happens when these equations collide. In the Friedmann equations, which describe cosmic expansion, dark energy's repulsive term eventually dominates as matter dilutes. The solution isn't just exponential growth, it's acceleration, where the emptier the universe gets, the faster it flies apart. Voids amplify this effect, their gravitational hills steepening as they expand, creating a feedback loop etched into differential equations. It's math predicting its own obsolescence, a future where galaxies vanish beyond event horizons, not of gravity, but of expansion. What's breathtaking isn't just that math describes nothingness, it's how beautifully the numbers align with reality. When astronomers measure supernova or map the cosmic microwave background, they're reverse engineering these equations, confirming that emptiness has structure, rules, even a kind of logic. The universe doesn't just tolerate voids, it computes them with a precision that humbles our brightest minds. In the end, the mathematics of nothing may be the most profound something of all. The cosmic story we tell is usually one of presence of stars igniting, galaxies colliding, matter clumping into the grand structures we admire. But flip the script and a far more intriguing narrative emerges. The universe is just as profoundly shaped by what isn't there. From the first microseconds after the Big Bang to the sprawling web of galaxies we see today, emptiness has been the silent architect, carving out the contours of existence with a sculptor's precision. Rewind to the universe's infancy, when quantum fluctuations, tiny ripples in the fabric of reality, were the only seeds of structure. The denser patches became galaxies, the sparser ones ballooned into voids. This wasn't random. The void's expansion acted like a cosmic chisel, herding matter into filaments and clusters through sheer gravitational repulsion. Picture a pot of boiling water. The bubbles aren't just empty spaces, they dictate how the surrounding water moves. In the same way, voids don't just exist between galaxies, they actively push them into place, shaping the cosmic web like invisible hands molding clay. Fast forward billions of years and dark energy takes center stage. As the universe expands, voids grow emptier, their gravitational hills steepening. This isn't passive drift, it's a feedback loop of cosmic proportions. The more space stretches, the more dark energy dominates, accelerating the void's growth. In turn, these expanding deserts shove galaxies faster apart, like a rising tide scattering driftwood. The result, a universe where structure isn't just built by gravity's pull, but by emptiness's push. The Virgo supercluster, our galactic neighborhood, isn't just a cluster of matter, it's a raft adrift in a sea of growing nothingness. Yet the void's legacy isn't just about the past or present, it's about the future. As dark energy's influence grows, voids will eventually dominate the cosmos. Galaxies outside our local group will vanish beyond an unreachable horizon, their light stretched into oblivion. The universe's epitaph won't be written in starlight, but in the cooling embers of isolation, where the distances between surviving matter become so vast that no future civilization will ever know the cosmos was once crowded. The lesson is humbling. We're conditioned to see reality as a collection of things: planets, stars, galaxies. But the universe insists otherwise. The voids between them aren't background. They're the canvas, the negative space that gives the positive its meaning. From quantum foam to cosmic webs, absence isn't just part of the story. It's the loom on which the tapestry is woven. And as we peer deeper into the dark, we're not just studying space, we're deciphering the signature of nothingness itself. As we've seen, the astrophysics of absence reveals that nothing is far from inert. It's the unseen hand shaping galaxies, driving expansion, and perhaps birthing new realities. The void is not a void at all, but a dynamic force that defies intuition. Next time you gaze at the night sky, remember, the darkness between the stars holds the universe's deepest secrets. If this journey through cosmic emptiness intrigued you, hit like, subscribe, and share your thoughts below. What's the most mind-bending idea you'll take away? Until next time, keep exploring the infinite mysteries of space. But before we go, let's take one last look at the bigger picture. The universe's grand narrative isn't just written in starlight, it's etched into the emptiness between them. Those vast cosmic voids, the quantum foam's restless energy, even the eerie pull of dark flow, all of them whisper the same truth: absence is an action, not an accident. It's the force that carved the cosmic web, the reason galaxies cluster into filaments instead of scattering uniformly. It's why the universe isn't just expanding, but accelerating, racing toward a future where darkness isn't the exception, but the rule. And yet, for all its power, nothingness remains the cosmos's greatest paradox. It's where black holes rewrite physics and virtual particles defy logic. It's where wormholes might hide and parallel universes could brush against our own. The void isn't empty. It's the universe's workshop, its stage, its canvas. Every time we peer deeper into the dark, we're reminded that the most profound mysteries aren't just about what we see, they're about what we don't. So here's to the void, the silent architect, the hidden engine, the great unknown. Whether you're an astrophysics enthusiast or just someone who loves to ponder the night sky, remember, the gaps in our knowledge, like the gaps between galaxies, aren't dead ends. They're invitations. The universe is far stranger, far richer, and far more mysterious than we've yet imagined. And the best part, the story isn't over. There's always more to discover, more to question, more to explore. Thanks for joining me on this journey through the astrophysics of absence. If you enjoyed this dive into cosmic nothingness, don't forget to like, subscribe, and let me know in the comments what's the one idea from today's video that's still spinning in your mind. Until next time, keep looking up and keep wondering. The universe